This process shows how benzene interacts with human biological molecules, especially enzymes. First, benzene typically enters the body through inhalation or skin contact, especially in polluted or industrial areas. Once inside, it travels to the liver, where an enzyme called CYP2E1 metabolically activates it. CYP2E1 converts benzene into reactive metabolites, mainly benzoquinone, which are far more harmful than benzene itself. These metabolites don't bind to normal receptors, instead, they attack cells indirectly. On the right, you can see the consequences of this activation. The reactive metabolites can bind covalently to proteins, inhibit enzymes, and disrupt detoxification pathways. This leads to oxidative stress, DNA damage, and ultimately, cell dysfunction and cell damage. In summary, benzene itself isn't the main danger. It's the reactive metabolites produced by CYP2E1 that become carcinogenic and harmful to the body.
Do you know that a common chemical found in cigarette smoke and gasoline, which is benzene, can form covalent bonds with your DNA? Let me explain the overall mechanism of how benzene becomes toxic in our body. First, when benzene enters the body, most commonly through inhalation from cigarette smoke or environmental exposure, it easily passes into the bloodstream because it is a small, lipophilic molecule. At this point, benzene itself is not yet the most dangerous form. Once inside the body, benzene is metabolically activated in the liver. Enzymes involved will convert it into several reactive metabolites, including benzene oxide, phenol, and hydroquinone. These metabolites are highly reactive and are the main contributors to toxicity. These activated metabolites then travel to the bone marrow, where they can directly attack DNA bases. They form DNA adducts, and they also generate oxidative stress, which causes DNA oxidation. Because of this, the structure of DNA becomes damaged. This DNA damage leads to several harmful cellular effects, such as replication gets blocked, RNA and protein synthesis is inhibited, and mutations accumulate, causing chromosome abnormalities. Altogether, these processes result in mutagenic events, which are often considered the first step towards cancer development, especially leukemia. So in summary, benzene enters and becomes reactive metabolites and then attacks DNA, which leads to mutation.
Benzene's main target is the bone marrow. It destroys hematopoietic stem cells, causing anemia, leukopenia, and thrombocytopenia. And over time, this significantly increases the risk of acute myeloid leukemia. It also affects the respiratory system, leading to airway irritation, coughing, wheezing, and shortness of breath. Severe exposure can even cause bronchitis or pulmonary edema. For the reproductive system, benzene disrupts fertility. Women may have irregular cycles, while men can have reduced sperm quality and chromosomal abnormalities. Finally, benzene weakens the immune system by lowering CD4 T cells, B cells, and natural killer cells, making the body more prone to infections and chronic inflammation. Overall, benzene causes multi-system toxicity, with bone marrow suppression being the most serious effect.
Next, I will briefly discuss some effective mitigation strategies to manage benzene exposure, especially for workplace safety and public health. The first mitigation strategy is the continuous exposure monitoring of benzene. This includes personal air monitors and biological markers like urinary SPMA to assess benzene levels. Besides that, engineering controls such as benzene recovery systems, sealed valves, and ventilation can also reduce emissions effectively. For workers' safety, personal protective equipment, including respirators and chemical-resistant gloves, is crucial during high-risk tasks. Risk assessment must identify hazards with strict adherence to occupational exposure limits to keep exposure below safe thresholds. Regular health surveillance and worker training ensure early detection and safe handling practices. Moving on for the public health strategies, on a broader scale, public awareness campaigns are crucial in educating communities on benzene sources and how to reduce exposure, such as avoiding smoking and minimizing gasoline engine use. And lastly, enforcing regulatory measures and compliance could ensure that industrial and vehicular benzene emissions are controlled to protect public health.
Do you know the story about the birth of benzene ring? In the 19th century, chemists couldn't explain benzene's formula and its unusual stability. Auguste Kekule, a chemistry professor, also tirelessly trying to solve the problem. Until one day, he daydreaming and saw a snake eating its own tail. Inspired by the vision, he began his research and proposed a breakthrough that changed chemistry: hexagonal ring of 6 carbon atoms.